Hello everyone, welcome back to another tutorial video on LlamaIndex. In this video, I'll help you understand the different indices available in LlamaIndex, which covers VectorStoreIndex, ListIndex, and KeyWordTableIndex. Additionally, we will even explore StorageContext and ServiceContext and learn how to effectively utilize them. So let's start with VectorStoreIndex. So in VectorStoreIndex, a document is divided into different chunks, and an embedding for each chunk is computed accordingly. We call this each chunk a node, which essentially corresponds to a chunk of text from a document. So LlamaIndex takes in document objects and internally parses or chunks them into node objects. And then the VectorStoreIndex stores each node and a corresponding embedding in a vector store. And during querying, a VectorStoreIndex involves fetching the top k similar nodes and passing those into the response-synthesis module. And let's see what happens in response-synthesis module. Let's say we have top k retrieved nodes based on similarity, and here k is 2. We pass query and text present in node 1 to LLM and ask it to answer the query. Let's now say this as answer 1. Now we pass query and existing answer 1 and text in node 2 to LLM and ask it to refine or update the answer. Since there are only 2 nodes available, this is the final response that is being generated for the query. If there are n nodes, this process is repeated for n number of nodes. So I think you all have understood the working of VectorStoreIndex. So let's go with the code and start implementing a simple query system with VectorStoreIndex. And this we have seen even in the previous video, but I'm still repeating it to have a flow in the overall video. So for this video, I'll be taking with the help of use of polygram essay text, which we'll be having in the LlamaIndex docs. So let's have that before going forward. In fact, there are different kind of data sources in this data. You can data folder in docs, so you can go and check about it. Just upload, create a new file and name it as txt. Just paste it. Done. So let's install LlamaIndex, and then probably I'll just go through the code. We'll have a simple directory reader from which with the data loader, we'll read the data present in the data folder, and we need an OpenAI key to follow this. So let's get the OpenAI key here. Then let's have it. So yeah, and then we are creating a VectorStoreIndex from the document that we'll be reading it from the polygram essay text. And then we can even give a parameter of similarity top k equal to 3. And earlier when I'm explaining, I've actually given top k as 2, but here I'm giving it as 3. You can even give 1 or 2 or 3 or 5 as well, whatever works for you. So let's start with this and let it run, and we should be able to have the response. Yeah. So for this, the author wrote stories and worked on IBM and TRS-80 and some other things. Yeah, based on this. And then also the response sensor in VectorStoreIndex may not have multiple rounds to LLM calls. So it only have will have those refinement process of calling the LLM calls repeatedly when the nodes exceeds the context window. So in vector store index, the refinement only happens in the situation where the context window is exceeded than the limit you have specified. So we will talk more about this during the later stages, but want to mention about it here to avoid the confusion. So we have vector store index built, and then we have seen starting building a QA system on top of that, right? So, but often once an index is built, we have been creating embeddings and using the OpenAI embeddings for each node back and right. But once an index is created, we don't want to repeatedly create the index because it involves cost operation. So how can we reuse the built index again and again? That's where storage context helps for these use cases. So let's start looking at what storage context is and learn more about it. So now let's say I want to use the previously built index repeatedly. And each time I want to query, I don't want to repeatedly build the index, right? As embeddings have to be created repeatedly. And the time and cost for doing all this process is pretty huge. Rather than that, it would be useful if you can save the index once it's created and load the index whenever you want to query. So LlamaIndex provides storage context abstraction to do this. The built index can be saved locally, that is, in memory, or it can be stored on MongoDB or Redis. So let's see how can we save and load the index. So let's start with understanding how you can code and save the index that we have created with the help of storage context. So for that, we'll import the storage context module, and we'll have doc store, index store, and vector stores, and that I have explained in the previous video. Please go and check out if you have missed that. And then we'll have the simple node parser to parse the given document. So first we'll get the nodes from by using the simple node parser from the loaded documents here that we have done earlier. And once we have done that, we'll initialize the storage context with the default doc store, vector store, and index store. And then we'll build a vector store index with the created nodes here, and having the storage context that whatever we have built, and then save the index. Let's run it. So with the index will be saved in the persistent directory storage here. So let's see. Yeah. And it has doc store, graph store, index store, and vector store JSON files. So I'll quickly recap what each of these actually contain. So vector store actually contains all the embeddings for each of the chunks or nodes created. And index store has all the metadata of information. And since this is not any graph index or something, graph store doesn't contain any information. And the doc store contains all the chunks data and then any metadata information of each chunk, what are the different metadata keys that you want to exclude and other things. So you can actually go and check out while you are running through the notebook. And then we have saved the index in the storage directory. Now we want to basically load the index. So for that, you need to again mention that where the index is actually saved in the persistent directory storage, and use the object load index from storage context to load the index. Once you load the index, you make a query engine, and we'll again ask the same question. Let's see what answer we'll get now. So yeah, yeah, I think we got the similar answer. So yes, that's what how you save the index. So once, so all this while we have actually created an index and made a QA system out of it, and we want to save the index and I can load the index as well. But there is something really important concept called service context, and how and why we want to use service context. So let's have it. Let me explain about service context more. Now we have seen building index and saving it and loading it and querying on top of it, right? But when generating an answer, I want to limit the number of output words or tokens I want to use. So tokens in LLM language, it's splitting of words probably. You can check it out what tokens are, which is out of scope of this video. And I want to use a specific LLM, say either OpenAI or Anthropic or Cohere or Inflection, or use OpenAI embedding model or open source sentence transfer models. I want to limit the number of tokens in each chunk as well. So how can we do that? So LlamaIndex has service context that helps for this. So there are different components in the service context that you can configure. So what is a different LLM, and then what is a text chunking that you want to basically fit into LLM context window through prompt helper, and then what is a different embedding model that you can use with the embed model, and you can even parse, convert your documents into nodes with the help of node parser, and there is a callback manager as well. So yeah, let's look into it. Before that, yeah, there are a couple of terms that you need to understand. So there is a chunk size. So chunk size is the size of the text chunk for a node. It is used when for the node parser, and chunk overlap is the amount of overlap between two nodes, with which you'll provide a parameter and it will accordingly chunk the nodes. And in the prompt helper, there is a context window parameter. This will tell the total context window of the LLM that we set for querying purpose or generating an answer purpose. What is the total context window that can fit into an LLM? And number of output is a maximum number of output tokens that we say ask the LLM to generate. And yeah, that's it. And then there is chunk overlap ratio as well, which is the percentage of chunk size of between which will tell how many number of tokens you can have a chunk overlap between two consecutive chunks or nodes. And then yeah, let's see how you can use them and in the index purposes. So earlier we were using GPT-3 and now let's use GPT-4 and have a max tokens for generating an output nodes answer. And let's fix chunk size 40 this time as than default value, and have a chunk overlap of 0 while creating chunks. And we have a context window of 4096. Let's keep the defaults, and you keep them in the service context, the LLM embedding model, parser, and then prompt helper. And once that is done, so we will be creating the index. Yeah, we should ideally be including this in your index creation, and then start querying the index accordingly. So let's see how it runs. And then I think it will take some time. Yeah. So yeah, you can see the difference between the older output and the current output. That happened because we actually changed the chunk size of 40. The default chunk size is, I guess, 1024, and there is a chunk overlap of 20, which I changed here. And the model is also changed, and even which I kept similar top K as 3, but still there is a change in the answer. So this is how it impacts. So you can actually change these different parameters and see what works for you. So that's how a service context helps. And next we'll go through two other indexes, which is ListIndex and KeyWordTableIndex. The ListIndex segments the given data into distinct sets of nodes and links them in a sequence. When a query is made, if no additional parameters are specified, the LlamaIndex straightforwardly loads all nodes in the list index into the response module. An alternative option is to use the similarity top k parameter, which retrieves the top k nodes based on embedding similarity. The ListIndex response engineer module, by default, if no parameters are given, a process similar to VectorStoreIndex response engine module is followed. This procedure operates across all nodes in the list index without any node filtering. In other words, suppose there are 5 nodes in the list index, as shown here. You begin by providing query and node 1 text information to the LLM and asking it to generate an answer. The LLM produces answer 1 in response. Next, you submit the query again, this time with node 2 information, asking the LLM to refine the initial answer 1 based on node 2 information. Now you get answer 2 from the LLM. In the similar way, this process is repeated across all the remaining nodes. And so answer 3 and answer 4 and answer 5 is generated. So the final answer is answer 5, which is generated by iterating through all 5 nodes. So now let's see how a list index can be used for the summarization purpose and how you can create the index. So let's import the list index module and then create index accordingly list index, and then have a query engine to query the index. So we specify a specific mode, response mode as tree summarize, which is specifically designed for summarization purpose. Since list index, for the list index, we go through all the nodes available and for a given query. So this kind of index is more suitable for summarization purpose. What is a summary of the given document? Since to generate a summary, you should always go through all the nodes. So, and tree summarize response instance mode is specifically designed for summarization purpose. So we ask the query, what is the summary of the document? So since it goes through all the nodes available, it will take quite a bit of time. Before that, as it goes through the process backend, let's see another parameter. Even though the default thing is going through all the nodes, we can still mention that I want to retrieve only top 2 nodes based on the similarity. So you can mention that in the similarity top 2k parameter, k equal to 2 as a parameter here, and have build a query engine accordingly. But yeah, in the above case, you can see that it has given a proper summary of what the author's experience writing essays and other things. Now we'll see what the summary will be when we just take top k equal to 2, most 2 similar nodes in the index. So the summary will obviously should change, but let's see how what kind of answer we'll be seeing here. And so after this, we'll be explaining what is keyword table index and how it is being created. So let's see. It's also taking a couple of time. Yeah. So yeah, here you can see it is more detailed because we have given top case similarity 2, and since it is taking only 2 nodes, there is more information present in it. And yeah, that's how you can use a list index for summarization purpose. In fact, you can use the same index by giving top case similarity 2 and probably have you have a query on top of the index as well. So the final thing is keyword table index. Let's first understand what keyword table index is. In keyword table index, it extracts keywords from each of the node and constructs a mapping from each keyword to the corresponding nodes that contain that keyword. So here there are 3 nodes, and we extract all the keywords from each of these 3 nodes, say NYC, city, population, climate, and politics. And all these keywords are mapped to their respective nodes from which they have been extracted. In keyword table index, during a query time, we extract relevant keywords from the query and match these with pre-extracted node keywords to retrieve the corresponding nodes. So here, for example, we extracted NYC and climate from the query, and these are present in node 1 and node 3. Now these retrieved nodes, node 1 and node 3, are sent to the response index module. And the process of generating an answer in the response index module follows the same as discussed in earlier indices. So now let's see how a keyword table index can be built, and on top of that, how you can start querying it. So we have keyword table index here, and we can create an index with the help of this. And then on top of that, we have an index query engine. And then let's start creating an index first. And then we have a question, which is the author complete his graduation from Stanford. And then see, while creating keyword table index, we use different NLTK modules to extract the keywords and from each node, and accordingly map keywords to each node, which is why it will take some time to create an index. So once the index is created, so when you are querying, it actually extract the keywords. Here the probable keyword is Stanford, and then so it will filter out the nodes which has Stanford as the word present in all the nodes, available nodes, and filter those nodes and gives it to the response index module to generate the final answer. So that's what happened in the backend here. And it says, no, the author did not actually complete his graduation from Stanford. And this is not even mentioned in the whole, filter nodes. So yeah, that's how we have seen a lot of things in this video, starting from VectorStoreIndex, StorageContext, service index, StorageContext, ServiceContext, and ListIndex and KeyWordTableIndex. So ListIndex is specifically useful for summarization purposes, and then KeyWordTableIndex is for extracting specific keywords, and on top of that, create some response in this model. So there are a lot of things that you can actually check in detail in the indices part. So there is a neat graphical representation and in the documentation to go through each index. And there is another index, tree index, which you can explore along with the indices which I have explained. And then even in the storage context part, so how can you store the index in AWS S3 or MongoDB or Redis, and how can you customize storage into different vector stores as well. Also, LlamaIndex has vector store integrations. So we have tight integrations with Pinecone, Quadrant, Waviate, vector stores. So you can check out how you can connect with them here. So here is an example of Pinecone, and you have all the examples of how to connect with them, like Pinecone and Waviate, and maybe in-memory index of files and other indexes. So please do check out how you can connect with them with the external vector DBs. And you can even check out the ServiceContext module here, and check all the different configurations available. And yeah, so even the different LLM parts or embeddings that you can use, how you can customize along with the ServiceContext, that you can check it here. So yeah, that's all for this video, and we'll meet with some more interesting content in the next tutorial video. Thank you.